Okay, so I'll start with a teaser, and here I'm showing a video of our algorithms. Our paper is about texture magnification, and we show it here for bilinear filtering with DLSS denoising. We have flip errors in the middle, where you should have as black image as possible. And I'll restart the video. And we have ground truth in the upper left corner, and then two algorithms that we've compared to. Our method is in the lower right corner, and as you can see, it has extremely low error. Nice thing about our technique is that it costs at most one texel per pixel, and often also zero error. So before I start with the algorithms, I'll cover some background. What we call one-tap SDF in this presentation and in the paper is a filtering after shading work with stochastic texture filtering by Pharr and others from last year. And the idea is very simple. Most of my examples will be with bilinear filtering. And so here we have 2x2 texels, and you have a sample point, let's say here. Then you can compute your bilinear filter weights as usual. And then SDF for stochastic texture filtering is simply stochastically selecting one texel, and you use the filter weights as probabilities. And you just choose that texel and use that as your result. This is a great paper, definitely recommended reading. And there's lots of good stuff about filtering after shading, which is really important stuff. So the second paper is what we call WaveCom SDF in my presentation here, and it's work by Wronski and others from May, so it's very recent, and the idea there is to sample one texel using SDF, one-tap SDF, and then weight them together. So we have this estimator, which I won't go into the details about, but basically you gather texels from neighboring pixels, and we do that in an inexpensive way using wave intrinsics on the GPU. And what we get is good performance and increased quality because we get new texels from the neighboring pixels. Sometimes this can be a little bit wasteful because sometimes you gather or you produce the same texels, or you fetch the same texels multiple times, which means that you don't get any new information. So we want to improve on that. And so primary motivation for our work is that recently a family of neural texture compression techniques have appeared, and those are kind of expensive, but usually high quality. And so our assumption is that we can afford at most one texel per pixel. So one-tap SDF and wave communication SDF are two solutions for that, but as you can see in the images here, we would like to get a little bit better quality than that. In fairness, I should say that those techniques are often used with some kind of denoising, so it could look a lot better than this, and I will show images of that later on. So before we dive into the algorithms, if I had been a really good researcher, I should have asked this question at the very start of our project, but it turned out that this was almost the last thing we did for our paper. So the question is, if you have bilinear filtering, how many unique texels are needed to achieve zero error when you do the filtering? And it was quite surprising, and we don't have a proof for this. This is experimental. We did this by looking at a textured quad at different rotations and magnification of 1. And quite surprising, you need less than or equal to 54 texels per wave if you have a 32-sized wave. And so that leads us to a question, what can you do with at most one texel per pixel? And it turns out you can do a lot with that. And that's what I'm going to talk about now. So our algorithms are called collaborative texture filtering. And as I said, the techniques, we have 3 techniques, and they produce a single texel per pixel. The rest comes from sharing within a wave, GPU wave, and we often have 0 error. We actually have 3 algorithms for this. The first one is called list merge. It's not very fast, so I won't talk about it much more, but it's interesting because it's the best possible solution in terms of how few texel evaluations you can get away with. Okay, so I'll talk about the basic algorithm flow for these techniques. And here I show with a toy example a GPU wave which is 8 lanes wide, configured as 2 by 4 pixels. And the first step is to have the lanes in the wave collaborate, so they find out exactly which texels are needed to get away with 0 error for your filter. And that gives you a unique texel set that this wave needs. Second step is to let each lane produce a texel. This could be neural decompression, for example, or whatever, procedural texture generation, for example. And then in the third step, each lane gathers the texel it needs from the lanes in the wave. And as an example, I'm showing the lane 0 here. It needs the red, green, blue, and white. And then it's weighted together, and maybe you get a pink pixel. And that's, of course, done in parallel for all the waves. And I'm just showing one more wave, the last one. But here you can see that the blue texel is shared between those 2 lanes. All right, so we skipped the first algorithm. The second algorithm is called box sampling. So here we walk through the steps 1, 2, 3 that I showed on the previous slides. And the first step here is to compute an axis-aligned bounding box around the 2 by 2. So again, the example is bilinear filtering. So we compute a bounding box around the 2 by 2 texels that we need for each lane. And then we use these wave active min and max, which are wave-wide functions that you can use to get the minimum over the entire wave. And for step 2 and 3, we need an invertible mapping from lane index to texel coordinates. So this is simply, a mapping from a 1-dimensional coordinate to a 2-dimensional coordinate. And everyone has done this a million times if you're programming graphics. Here you need actually to subtract the upper left corner, but it's very simple. And as you can see, there are some gray pieces here as well. Those are actually not texels that we need, but we fetch them anyway in this algorithm. So the step 2 is to let each lane produce corresponding texel. So we use this mapping function that I told you about. So lane 0 produces texel 3, 1, and so on. And when all lanes have produced their texels, we need to let each lane fetch the 2 by 2 texel it needs. So for example, for this pixel C, we need these 4 texels, and then we use the inverse mapping function. So for 2 maps to lane 5, so then we fetch that texel value by using a function called wave read lane at to get that texel value. And then we do that for all of those 4. And finally, we weight them together to get the 0 error result. So next I'll show, I'll describe algorithm 3, which is a little bit better at exploiting or at doing useful work in all the lanes. So for example, if the texel grid is rotated, for example, 45 degrees compared to the pixel grid, then you can get lots of unused lanes in this method. But the next one, called mask sampling, doesn't do that. And it works like this. Step 1, we need to find out which texels are needed for 0 error filtering. We compute a box, as in box sampling. And then for each lane, we create a local 2D bit mask where we basically stamp out the 2 by 2 texels that are needed by the lane. And so for pixel A here, and again, we've subtracted the upper left corner. we just mark the 2x2 bits in the bit mask here. And then we can do a wave OR over these bit masks, and that gives us a bit mask which holds all the unique texels that are needed by this wave. So similar to box sampling, we need a mapping to go back and forth between the lane index and texel coordinates. And so we enumerate only the texel lanes that we actually need, or sorry, we enumerate only the lanes whose corresponding texels we need, and those are the ones inside the green area. This mapping function is a little bit more complex. So for lane to texel coordinates, we use a find and set bit, and the inverse is counting set bits on one side of the texel coordinate. In practice, we use an 11 by 11 bit mask using 2 unsigned int 64s. And then step 2 and 3 are done exactly as in box sampling, except that we use the mapping shown above here. So what happens when we are not able to produce zero error? So it can happen that we cannot deliver zero error with at most one texel evaluation per lane, and in those cases we resort to what we call fallback methods, and we still only use at most one texel per lane, but the quality becomes a little bit lower. And we have a basic method denoted by C, and what we do is that we let each lane produce a texel using one tap STF, and then we gather texels from 3x3 neighbors and weight them together using this function. And so the first part here is just a weighting of the gathered texels that we have. We might not get all the ones we need, and then we have an extra term that reduces error a bit. You have to look at the paper for the details. We have also an extended method called C+, and it's a bit similar, but it also exploits lanes that have no useful texels to evaluate. You have to look at the paper for the details. All right, I'll switch to results. I have some visual results for bilinear filtering. This is a very simple scene. In the red square, we have zoomed in on a region which has actually zero error for our method, but the yellow one is a region, 32 by 32 pixel region, which has the most error with our method. And we have error metrics, PSNR, which should be as high as possible, flip should be low, color video VDP should be 10 at most. And then we have, so the first row is not denoised, and then it's denoised here. And you can see that we have really high quality with our method. And then we can also handle higher order filters, like, for example, bicubic Catmull-Rom filtering. And here is not denoised. And I should say that Wavecom STF does not handle negative weights, which Catmull-Rom has, so it cannot handle this case. And again, we have a quite high quality here for our method. And an important thing here is that one tap STF actually needs 2 texels per pixel because of the fact that they use a technique called positivization. Our method uses less than or at most 1 texel per lane. Okay, so how often do we actually need the fallback methods? And this is for bilinear filtering again. Alternatively, you can ask the question, how often do we get zero error? So we did this experiment where we had a quad again. We could change the rotation, which is x-axis, and we could change the magnification on the y-axis, which is shown on the y-axis. And so you want as little area as possible in this diagram. And some observation, box sampling is a little bit more rotationally sensitive than mask sampling because we have this peak here in the middle. And mask sampling and list merge are identical, which means that you cannot improve mask sampling anymore. The really important takeaway, though, is that you can see that box sampling above 2.35, you actually have zero error always. And for mask sampling, this happens even earlier at 1.59. And that 1.59 means that a texel is enlarged to cover 1.59 pixels. So it's not a lot. Image quality, here you can see those factors again. At 1.59, the PSNR goes up to infinity, which means 0 error. And you can see that box sampling takes a little bit longer. And we also have, our methods have higher PSNR, even at low magnification factors, where we have this fallback method. Performance, I'm not going to talk a lot about this, but the results are shown in microseconds per megapixel. So in a sense, all of the methods are really fast. And in parentheses here, we have the fallback methods. And the second parenthesis is average over this magnification range. And you can see those, you can actually see that, at magnification factor close to 1.6, we get 0 error, and before that, the fallback method shows up, which is a little bit more expensive. But still, compared to a full frame, which take 4,700 microseconds, 8.4 is not that much. We did some neural texture compression experiments. This is a super brief evaluation. We downloaded the NTC SDK. I made sure that all pixels in a scene that were rendered were magnified at least 2.35. And when we tried with NTC, one NTC texel and one tap SDF, the result was 89 microseconds per megapixel. But then the result is quite noisy. With our method, we got 93 microseconds, so it's a little bit more expensive, but not that much. When we did 2x2 NTC texels, however, this is classic bilinear filtering, but done in software. It was a lot more expensive. But yeah, case 2 and 3 have exactly the same quality in this case. Okay, so we have another expensive decompressor example. This is DCT decompression, where we basically do an 8x8 matrix multiplication per component. So usually it works like this. We do the red components, then green, then blue. However, we can actually sometimes exploit this to get a performance increase sometimes. And it's because our algorithms can actually detect which lanes do not have any useful work that it needs to be doing. So in this toy example, let's assume that we only need 2 texels for lane 0 and 1. So normally we could decompress red, green, blue like this, but we could also do like a classical vertical to horizontal transformation. And then we assemble the RGBs, and the performance gain is a difference here. And we have seen up to 2.5 times in terms of speed up. So this is very preliminary, non-extensive results, but at least we have a proof of concept in place. So how do we make a good algorithm recommendation? Pareto diagrams are excellent at this, I think, if you want to find the most quality performance efficient methods. And I must say that I have not used them that many times myself, but I should have, and I will try to do that more in the future. So the Pareto, in this case, we have runtime cost on the x-axis, we have PSNR quality on the y-axis. So you want to be to the left on the x-axis, you want to be high on the y-axis. So therefore, the red curve here is a Pareto curve. So the recommendation is, in general, box sampling with our own fallbacks, and sometimes mask sampling can be the recommendation if you want to go after more performance, which we did, for example, in this DCT example. So conclusions and future work. Again, I mean, if I had been a good researcher, we might have been able to reach this point probably a year earlier. But research is seldom a straight path, and at least we got here in the end. I think we have addressed the shortcomings of stochastic texture filtering for magnification. And I'd like to think of our work as a clever per wave cache for magnification. We get 0 error above certain magnification factors with 1 texel per lane. We handle bicubic filters with both negative and positive weights, and I'm not sure I ever want to look at bilinear filtering again, because those bicubic filters are really nice looking. Yeah, there's pseudocode in the supplemental for future work. We have some ideas, but we are already working on minification, and we have some initial results there. And I'll show you a video, and I'm thinking I'm out of time, but yeah, I can start taking questions maybe. But in this video, we have a ground truth filtered image in the upper left, we have magnification factor, and then we have the box sampling in the lower left and mask in the lower right. And the brown waves here are such that you need to call the fallback method. So the mask sampling doesn't need to do that very often. And then I'll just let the video run. And I guess I can take questions.
Okay, again, probably 2 questions.
Always, Karsten.
Sorry about that. Fascinating talk. Can you comment on when you have divergent control flow, right, in a path tracer, and you need to sample the texture? How do you deal with that? Do you switch into a, let's say, a serialization mode where you process only the active lanes and then use the full lane to do the textures, or how do you deal with that?
I'm not sure I understand.
So if you have a lot of divergent control flow, right?
Okay.
For example, in a path tracer, right? And somewhere you need to query the texture, right? How do you get the wave information back, essentially?
I'm not sure.
Okay, maybe take it offline, sorry.
Can we take it afterwards?
Yeah, sure.
Okay, sorry.
This work? Okay. Hello, great talk. I was wondering, so you mentioned this is sort of a local cache written in software. Do you have any insight into whether this affects the need for conventional, tiling formats inside the driver? Harder specific formats? Could we get away with simpler or perhaps linearly laid out images in memory, because now we're taking care of the caching in software?
Yeah, I haven't thought about that either, actually. Yeah, sorry.
So the main benefits here are that you save on the sample cost, right?
Yeah, exactly. So we want to get away with, at most 1 texel evaluation or 1 texel decompressed per lane. And so what was the question after that?
So I was wondering, so in GPUs, they have these texture formats that are quite complicated instead of just having the pixels be linear in memory. And I was wondering whether that sort of obviates the need for that to a degree, and maybe you could have simpler texture formats that are more predictable.
Yeah, I don't know. I'm drawing a blank here. Sorry.
Okay, thanks.
Any more? Then I have one. So there are 3 ways of using that one. Then there's a fallback method. Then yeah, it definitely bad for performance, and I would just pick the approximate one, so just using that filtering, even though that's not perfect.
Yeah, I mean, you can do that, of course, also. And we have evaluated that in the paper. I actually have some slides on that as well. But we show in the paper that we have higher quality than previous methods, even if we use only the fallback methods. So that, yeah, you can do that as well. But then you never get 0 error. Yeah.
Okay, thank you. Yeah, let's thank the speaker again.